Let's take a look at transformations in simple linear regression. Recall the assumed linear regression model, where y is assumed to have this linear relationship with x. But of course, not all relationships start out linear. Sometimes, though, we can find an appropriate transformation of the data that results in this assumed linear model being reasonable. Let's take a look at an example. Here we have brain weight versus body weight for 99 species of mammal. And a couple of points of interest here: dolphin brain weight and human brain weight is much larger than would be predicted simply from their body weight. But the point of interest here is seeing if we can find a relationship between these variables. And this line that we fit through these points certainly doesn't adequately summarize the relationship. So a linear relationship would not be a reasonable assumption here. But let's see what happens when we take the log of brain weight and plot that against the log of body weight. Here I've taken the log of brain weight and the log of body weight, or in other words, I've applied a logarithmic transformation to both brain weight and body weight and plotted it out in a scatter plot. I've used natural logs here, but we get a similar type of plot if we used logarithms with a base of 10 or any other base. And here this logarithmic transformation has resulted in a very straight line. So in this situation, if we did a regression of log of brain weight on log of body weight, that might be a very reasonable thing to do. So some relationships can be made linear by an appropriate transformation of the data. And by transformation, we simply mean that we are applying some function to our data values. Common transformations include the log, the square root, and the reciprocal, but we could do a variety of other ones as well. We can transform the response variable, the explanatory variable, or both. Now let's take a look at another example. Here's an example I looked at previously that involved 36 species of Australian timber, and we related this hardness, which is a measure of the durability of the wood, to the density of the wood. And we fit a line through those points, and an assumed linear relationship is certainly not the worst model in the world. But when we plotted the residuals for this model, there's this clear curvature here. And as well, there appears to be increasing variance as we go along. The variability of the residuals is increasing as density increases. And so that common variance assumption of our model appears to be violated here as well. Well, when we have a situation like this where there is curvature and there is increasing variance, very often a transformation of the response variable might take care of that. A common transformation we might try is a log transformation, so let's see what happens when we try that. Here I've plotted the log of hardness against density, and this doesn't seem to be fitting all that well. We can see with the naked eye here that there is some curvature. And if we look at the residual plot, that curvature becomes a little bit more obvious. So when we use the log transformation, we may have overcooked things a little bit. Now the curvature is in the other direction. So we might try, suppose, the square root transformation. The square root transformation isn't quite as strong a transformation as the log transformation. Let's see what happens when we fit that. Here I've plotted the square root of hardness against density. And that's starting to look pretty good. Well, let's see what the residual plot looks like. The residual plot doesn't show any obvious curvature here. There does appear to possibly be lower variance down here than up here. We might have a problem with increasing variance, but there is no curvature, and overall this transformed model appears to be a little bit better than that original untransformed model. So that leads us to this possible model, where we use the transformed value of hardness and say that the square root of hardness has this linear relationship with x. If we went back to the original data here and plotted hardness against density, and we calculated the coefficient of determination r squared, we'd see that that's approximately 0.95. Now that's a pretty big value of r squared and does say that there's a very strong linear relationship between hardness and density. But we saw that curvature in the residuals and we said that we can do better. So we transformed hardness using the square root transformation. And if we were to fit the square root of hardness against density and calculate the coefficient of determination, we'd see that r squared is approximately 0.97. So our coefficient of determination has gotten even greater. There's an even stronger linear relationship between these variables. To fit this model, we would simply take the square root of those hardness values and call the square rooted hardness values our y values, and then just fit the model in the usual way. I've done that here and fit in this least squares regression line. So let's see what the slope and intercept of that line are. Here's our estimated regression line, and I have a big hat here representing that this is the predicted square root of hardness is equal to this least squares regression line when the square root of hardness is called our y variable and our density is called the x variable. And we could, if we so desired, use this relationship for prediction. What is the predicted hardness for a density of 60 pounds per cubic foot? Well, 60 is our x variable, and we're simply going to put 60 into this line. And so the predicted value of the square root of hardness is equal to this. And we work that out and we get approximately 47.739. But typically we want to predict the hardness itself. And so if we wanted the predicted value of hardness, well, we're just going to undo that transformation and say the predicted value of hardness is simply going to be the square of 47.739, and that is approximately 2,279. Sometimes there are mathematical justifications for choosing a particular transformation. Other times we might simply use trial and error. We might experiment a little bit, try a few different transformations on our different variables in an attempt to find a relationship that satisfies the assumptions of the simple linear regression model. We want to find a relationship that is approximately linear, one that has approximately constant variance, and one for which the normality assumption is reasonable as well. And so we might try a few different possible models before we find one that we feel is reasonable. And for some datasets, the simple linear regression model simply isn't going to cut it, and we're going to need to use more advanced modeling techniques.